Most computer graphics seen in animated movies or computer games are based on three-dimensional models. A 3D model of an object is composed of hundreds or even thousands of tiny primitive shapes, such as triangles or rectangles. Each corner of a model, that is, each vertex, is encoded as a vector. Using matrices to transform these vectors is an essential aspect of computer graphics. There are several different types of transformation possible, including scaling, translation, rotation, reflection, and shearing. In this video, I'm going to look at three of these in particular: scaling, translation, and rotation. To illustrate the concepts, I'm going to begin with only 2 dimensions for now, but later you'll see that the same principles apply in 3 dimensions as well. Consider then this triangle. Imagine it's part of a much larger model composed of hundreds of other triangles. Each corner of the triangle, that is, each vertex, is described by a vector with an x-coordinate and a y-coordinate. To make this triangle twice as big, we can scale each of the vectors by a factor of 2 in the x and y dimensions. This is easily done. It's just a matter of multiplying each of the original vectors by another which specifies the scaling operation we want to perform. In this case, we can multiply each of the original vectors by the vector 2, 2. The result is a triangle which is twice as big. If we want to double the size of the triangle in, say, the y dimension only, we can use the same technique. But this time we multiply each of the original vectors by the vector 1, 2. The effect is to stretch the original triangle. To translate the triangle, that is, to move it somewhere else, without changing its size or shape, we need to add a vector to each of the original vectors. For example, to move the triangle 3 places to the right and 4 places up, we add the vector 3, 4. And here's the triangle in its new position. So as you can see, scaling and translating vectors are simple operations. But rotating a vector with respect to the origin is not quite so simple. We need a way to calculate the coordinates of each new vector based on the coordinates of the original vectors and the angle of rotation. We can use trigonometry to derive a method. We'll focus on just one of the original vectors for now, and we'll refer to its coordinates in general terms as x0 and y0. Now, suppose we want to rotate this vector 30 degrees anti-clockwise. We'll refer to the coordinates of the new vector, that is, the values that we need to calculate, as x1 and y1. Notice that the original vector forms a right-angled triangle. We'll refer to the length of the hypotenuse as r, and we'll call this angle alpha. We know the length of the adjacent side. It's the x-coordinate of the vector, x0. And we know the length of the opposite side. It's y0. These well-known trigonometric identities allow us to express x0 and y0 in terms of r and alpha. Now, consider the right-angled triangle formed when the original vector is rotated through an angle of beta degrees. The length of the hypotenuse is the same as it was before, namely r. The length of the adjacent side is given by the x1 coordinate, and the opposite side is y1. But notice that the internal angle of this triangle is actually alpha plus beta. By applying the same trigonometric identities again, we can now express x1 and y1 in terms of alpha and beta. To turn these expressions into a pair of formulas that we can use to calculate the new vector coordinates, we're going to need some more trigonometric identities, namely Ptolemy's sum and difference formulas. These trigonometric identities were derived about 2,000 years ago by an Egyptian astronomer and mathematician known as Ptolemy. We won't concern ourselves with their derivation here. Suffice to say, these formulas are identities because they are always true. So, given that x1 is equal to r multiplied by cos alpha plus beta, one of Ptolemy's identities allows us to substitute the term cos alpha plus beta with this term instead. Now we can expand the brackets to multiply both terms inside by r, and since we've already shown that x0 is equal to r cos alpha and y0 is equal to r sin alpha, we can write a new expression for x1, like this. In the same way, if y1 is equal to r multiplied by sin alpha plus beta, we can employ another one of Ptolemy's identities, like so. Again, we multiply by r throughout, and then we can write a new expression for y1 in terms of the original coordinates, like this. Now we can use our new formulas to rotate these three vectors 30 degrees anti-clockwise. First, vector A, then B, and then C. Let's attempt to describe this type of transformation using a matrix. First, we'll make a slight adjustment to the second equation. And suppose for a moment that we can describe this pair of equations in a table like this. To calculate x1, we can multiply x0 by cos beta, and then we can add y0 multiplied by minus sin beta. That's exactly what our first equation does. To calculate y1, we can multiply x0 by sin beta, and then we add y0 multiplied by cos beta. That's what the second equation does. If you watched the previous video in this series, then you may have realised that this is the same order of operations for multiplying a matrix by a vector. In other words, we can rotate a set of vectors through the same angle by multiplying each vector by the same matrix. Let's see another example, using our newly derived rotation matrix. We're going to rotate each of these three vectors through an angle of 90 degrees. First, we need to prepare the rotation matrix for an angle of 90 degrees. If you use a calculator or look up these values online, you'll find that the cosine of 90 degrees is 0 and that the sine of 90 degrees is 1. Notice that we need to put minus 1 in the top right of the matrix. All we need to do now is calculate the product of the original vector and the rotation matrix. First for vector A, then vector B, and finally vector C. At the start of this video, you saw that we can scale a set of vectors by simply multiplying each vector by another vector. Well, we can perform the same operation using a scaling matrix instead. If you check these calculations, you'll see that the product of each original vector and the scaling matrix gives us the same coordinates for the new vector. Now, it might seem as though we're complicating the calculation unnecessarily. Multiplying two vectors together is much easier than multiplying a vector by a matrix. But by doing it this way, we can take advantage of a very special property of matrix multiplication. Suppose, for example, that we want to rotate a vector through 90 degrees and scale it by a factor of 2 in just one operation. This is the matrix we would use to rotate the vector through 90 degrees, and this is the matrix we would use to scale it by a factor of 2 in both the x and y dimensions. Multiplying them together gives us one new matrix that encodes both transformations. Now we can apply this combined transformation matrix to each vector. You can see that the original triangle is both rotated and enlarged. But it doesn't stop there. This technique can be used to combine any number of different transformations into a single matrix. All you need to do is multiply the individual transformation matrices together. After that, just one matrix operation can be applied to every vertex in the model. In order to perform translation, as well as rotation and scaling, using a single transformation matrix, we need to make some adjustments to this technique. At the start of this video, you saw that we can translate a vector by adding another vector. In order to translate a vector using a matrix, we need to come up with a matrix that can be multiplied by the vector. We can't perform an addition operation because you can only add together a pair of matrices or a pair of vectors if they have the same number of rows and columns. But coming up with a two-dimensional translation matrix is problematic. We need to employ a mathematical trick. First, we have to change the way we encode the vertices in our model. Each original vector is given an additional component, the number 1. These extra components have nothing to do with the spatial coordinates of the vectors. These are still vectors in two-dimensional space. Then we need a translation matrix with 3 rows and 3 columns. Notice that the desired changes to x and y are specified in the top 2 rows of the 3rd column. The rest of the matrix will be the same for any two-dimensional translation. Now, if we calculate the product of each original vector and our new translation matrix, we will get the desired translation. The clever positioning of the 1s and 0s ensures that we achieve the same effect as adding 2 vectors together, but we achieve it using matrix vector multiplication. But of course, each new vector has an additional component, the number 1. We can easily ignore this when we plot the new positions of the vertices. You'd be forgiven for thinking this is a lot of extra work to perform a translation that could have been done by simply adding a couple of vectors together. But remember, any number of different transformations that can be done with matrix multiplication can be combined together into a single multiplication operation. We do need to make some minor changes to our scaling and rotation matrices to allow them to be combined with the translation matrix, but as you can see, it's just an extra row and an extra column to ensure that the rules of matrix multiplication are still obeyed. So let's put this to the test. Suppose we want to translate each vector by 2 in the x direction and 3 in the y direction. Then rotate each vector through 90 degrees. Then scale each vector by a factor of 0.5 in both the x and y directions. And we want to do all of this in a single operation. This is the rotation matrix we're going to need. This is the translation matrix, and this is the matrix we need to scale the vectors. The order in which the matrices are multiplied together is very important. Matrix multiplication is not commutative. Matrix A times matrix B is not the same as matrix B times matrix A. Examine the triangle and you can see that if you translate it before you rotate it, then it will end up in a different place than if you rotated it before you translated it. Furthermore, to perform the 3 transformations in the order that we want, we need to multiply the matrices together in a different order. So, first we'll multiply the rotation matrix by the translation matrix. Then we'll multiply the scaling matrix by their product. And now the combined transformation matrix can be applied to each vector in the model. This, by the way, is exactly what a graphics processing unit is optimized to do. Matrix-matrix multiplication and matrix-vector multiplication. The same basic operations applied to thousands of vertices in a model, and all at once. High-quality, real-time animation of computer graphics depends on it. In the next video of this series, I'll show you how transformation matrices similar to these can be applied to a three-dimensional model.